Here we have a set of questions where we're looking conceptually and mathematically at entropy. The first set is just predicting the sign. Are we increasing or decreasing based upon what we know about our starting and ending components? Here we're going from H2O gas to liquid, from steam to water. That would be a decrease in entropy. When we have a gas, we have free moving random particles. And when it goes to the liquid state, they're much more close together. They're much more attracted to one another, and they become much more orderly because of that proximity to one another. When solid carbon dioxide, which we would call dry ice, sublimes, remember sublime means go from solid straight to gas. So that is a positive. That is an increase in disorder. The molecules were very orderly in that solid crystal and are very disorderly or very random as they go to the gaseous state. In this one, we have N2O making nitrogen and oxygen, 2 molecules breaking into 3. So for a couple reasons here, we can describe that as a positive delta S. A larger thing made of more atoms breaks into things with fewer atoms, and 2 molecules breaks into 3. Those smaller molecules now can move around more freely, can move around more randomly, and can arrange themselves in more different ways. An increase in dispersal of energy, but of randomness and disorder. And then here we have a combustion reaction. We look at states of matter and we look at coefficients. We start off with 27 as our total coefficients over here, 34 over here. That shows more particles, and they're also smaller in terms of the subscripts. Also, I go from a liquid to gases. Both of those support the fact that we are increasing the dispersal of energy, increasing the randomness, and increasing the disorder. When we are looking at this, probably the number one thing, which is why it was shown in this order in the notes, is the state of matter. State of matter, that difference between gas to liquid and liquid to solid, is the biggest difference in terms of how the particles are arranged. On B, I have some absolute entropy values. These would be found in the back of a textbook in the index section or in an AP question right within the problem itself. So we've got a whole bunch of values, and then we're just applying them down here. Remember, the delta S is products minus reactants, an equation that we're given. We do need to pay attention to the coefficients, but other than that, we're just plugging our numbers in. So I have 2 for my nitrogens, 1 oxygens, and 2 dinitrogen monoxides. The value comes up as a positive value here, which makes sense with our prediction. Here, we also get a positive value and an even bigger positive value than the previous because we did have the change of state in addition to a bigger increase in the number of molecules. So hopefully, whenever we do math, that can support and prove our predictions correct. Some other questions here are related to these numbers. The first one, CO2, which is up here, 213.8, compared to H2O, which is 188.8. So we have a difference there of about 30, maybe 25 joules per mole. Both of those are in the same state of matter, which is why they're fairly close. But when we think of CO2 compared to H2O, the CO2 atom molecule still has just 3 atoms, just like the water has 3 atoms. But within those atoms, we have more electrons. Electrons are the things that are moving around randomly and freely within a molecule. So even when we have an individual substance, we can know that it has entropy based upon vibrations within the bonding, based upon the movement of electrons within that. The only way to get to that minimum absolute zero in terms of entropy is a pure crystalline solid at absolute zero. We've got our atoms or our ions arranged perfectly in order with no motion in terms of our electrons there. So although they're both similar here, that molecule that's a little bit bigger in terms of atomic size and radius, and bigger more so in terms of electrons, is going to be able to be more random. Here, we don't have the values, but we are told NaCl aqueous, salt water, has a greater standard entropy than pure water or pure salt. And that's because here we have a crystal with a nice, neat, orderly arrangement. Here I have a pure liquid that is still close together and somewhat not orderly, but predictable in terms of its arrangements because of the IMFs. When I put my NaCl in there, I am breaking apart my waters, I am breaking apart my solids, and I'm putting them between there. There is some orderliness as the cations and anions are hydrated by the water, but it is still more random than the two separate, neatly arranged things. We have more than one type of particle mixed together and moving freely.